Today we are going to study permutation group. So we start with the permutation of set A. Okay. So definition of permutation of set A. Okay. Definition of permutation of set A. So a permutation of set A is a function from A to A. A permutation of set A is a function from A to A itself. Okay, that is both 1 to 1 and onto. So 1 to 1 and onto. So permutation of set A is a function from set A to A itself. Now we take the next definition. Permutation group. Permutation group. A permutation group of set A is the set of permutations of A that forms a group under the function composition. Okay, so permutation group of set A is the set of permutations of A that forms a group under the function composition here. Okay, so this is the definition of permutation. Now we take the example. We define a permutation alpha on set 1, 2, 3, 4 by specifying alpha of 1 equals to 2, alpha of 2 equals to 3, alpha of 3 equals to 4, and alpha equals to 1 and alpha of 4 equals to 4. So see here we define a permutation alpha on set 1, 2, 3, 4 by specifying alpha of 1 equals to 2, alpha of 2 equals to 3 and alpha of 3 equals to 1 and alpha of 4 equals to 4 here. We express this permutation in array form as, so here we want to express this permutation in array form. So array form alpha equals to, so write down first the elements of set 1, 2, 3 and 4. Now alpha of 1 is 2. So here below 1 alpha of 1 2. So below entry 1 write entry of alpha of 1. So alpha of 1 is here 2. So we write here 2. Now below 2 we write alpha of 2. So alpha of 2 equals to 3. So 3 here. Alpha of 3 equals to 1. So write below value of alpha of 3. And below 4 write the value of alpha of 4. So alpha of 4 equals to 4. So this is called the permutation alpha in array form. So 1 maps to 2, 2 maps to 3, 3 maps to 1 and 4 maps to 4. So all of you get it how to express the permutation alpha in array form. Okay. So that means here, see here, 1, 2, 3, 4, alpha of 1, alpha of 2, alpha of 3 and alpha of 4. So below entry J we write alpha of J for each J. Okay. So this is the permutation in array form. So I think all of you get it this. Now we see the next point, composition. Composition of permutation. Composition of permutation. So see here, composition of permutation. Composition of permutation expressed in array notation is carried out from right to left. Is carried out from right to left by going from top to bottom and then again from top to bottom. So remember this thing, the composition of permutation in array notation is carried out from right to left and by going from top to bottom and then again from top to bottom. So remember this, right to left and then top to bottom. So if you get this thing, then you will get the composition of permutation. Okay. So we take example. Alpha equals to 1, 2, 3, 4, 2, 4, 3, 1 and beta equals to 1, 2, 3, 4, 4, 1, 2, 3. Okay. So compute alpha beta and beta alpha. Now we see the definition of composition of permutation. Now we see the example. So composition of permutation is carried out from right to left and by going from top to bottom and then again from top to bottom. So we apply this here for finding the composition. So first alpha beta. So write down in order alpha and then beta. 1, 2, 3, 4, then 2, 4, 3, 1 and beta 1, 2, 3, 4, 4, 1, 2, 3. Now see here, composition of permutation carried out from right to left. So from right side we start from 1. Now here 1 maps to 4 and now then going left side and here from top 4 maps to 1. 1 maps to 4 and 4 maps to 1 here. So 1 maps to 1. Get it this? So that means we get alpha beta of 1 is equals to 1. So see here, alpha beta of 1 is equals to alpha of beta 1. Here beta of 1 is 4. So we substitute here 4. Now we want to find alpha of 4. So alpha of 4 is equals to 1. So that's why we get alpha beta of 1 is equals to 1. So this is by composition, and again by array we get the same. 1 maps to 4 and 4 maps to 1. So that means 1 maps to 1 here. So here in array notation, alpha beta 1, 2, 3, 4. 1 maps to 4 and 4 maps to 1. So 1 maps to 1. In similar way, 2 maps to 1 and here 1 maps to 2. So 2 maps to 2. Now 3 maps to 2 and 2 maps to 4. So that means 3 maps to 4. Now 4 maps to 3 and 3 maps to 3. So 4 maps to 3 again. So all of you get it from right to left and then top to bottom. So we get alpha beta. Now in similar way we find beta alpha. So write down first beta 1, 2, 3, 4, then 4, 1, 2, 3 and alpha now in similar manner from right to left, top to bottom. So here 1 maps to 2 and 2 maps to 1. So 1 maps to 1 here. So we get beta alpha equals to 1 maps to 2, 2 maps to 1. Then 2 maps to 4 and 4 maps to 3. So that means 2 maps to 3. Now 3 maps to 3 and 3 maps to 2. So 3 maps to 2 here. And 4 maps to 1, 1 maps to 4. So again 4 maps to 4. So all of you get it how to find composition of permutation. So here we get beta alpha. Okay. From right to left and then top to bottom. Remember this thing. Okay. Now observe this alpha beta and beta alpha. So here 1 maps to 1, 2 maps to 2, 3 maps to 4 and 4 maps to 3 in alpha beta. And in beta alpha 1 maps to 1, 2 maps to 3, 3 maps to 2 and 4 maps to 4. So by observing alpha beta and beta alpha, we get alpha beta is not equals to beta alpha. So the function composition operation is not commutative in a permutation group, and hence it is permutation group is not abelian. All of you get it this? So write down note. So right here we write a note. Alpha beta is not equals to beta alpha. That is the function composition operation is not commutative in a permutation group. Hence permutation group is not abelian. Is not abelian. Okay, all of you get it this? Now next point, inverse of permutation. Inverse of permutation. So here we take directly example. So see here, alpha is equals to 1, 2, 3, 4, 4, 1, 2, 3. So this is alpha. Find alpha inverse. So here we want to find the inverse of this permutation. So see here, alpha of 1, 4. Alpha of 2, 1. Alpha of 3, 2. And alpha of 4, 3. So here we want to find inverse. So solution, alpha inverse of, see here, alpha inverse of 4 is equals to 1. Alpha inverse of 1, 2. Alpha inverse of 1, 2. Alpha inverse of 2, 3. And alpha inverse of 3, 4. Okay, so first of all, write down the inverse of alpha 4, alpha 1, inverse of alpha inverse of 4, alpha inverse of 1, alpha inverse of 2, alpha inverse of 3. So that is alpha inverse of 4 is 1, alpha inverse of 1 is 2, alpha inverse of 2 is 3, and alpha inverse of 3 is 4. Now write down here alpha inverse. So first of all, write down 1, 2, 3, 4, and then write down inverse of item below the I. So see here, alpha inverse of 1, alpha inverse of 1 is 2, so write down 2. Alpha inverse of 2, 3. Alpha inverse of 3, 4. And alpha inverse of 4, 1. So this is the inverse of permutation alpha. All of you get it this? Okay. Now next point, symmetric group. Definition of symmetric group. Let set A equals to 1, 2, 3, so on up to n. The set of all permutations on A is called symmetric group of degree n. And it is denoted by Sn. Okay, so set A 1, 2, 3 up to n, the set of all permutations on A is called symmetric group of degree n, and it is denoted by Sn. So here we write a note. Let alpha be a permutation in Sn. Alpha be a permutation in Sn. We can define alpha of 1 in n ways. Let alpha be a permutation in Sn. So we can define alpha of 1 in n ways. Once we define alpha of 1, then we have n minus 1 choices for alpha of 2. N minus 1 choices for alpha of 2. Similarly, we have n minus 2 choices for alpha of 3. Continuing in same way, we see that the number of permutations in Sn is n into n minus 1 into n minus 2, so on up to 2 into 1. So here we know that n into n minus 1 into n minus 2 into so on up to 2 into 1. So this is nothing but n factorial. That means we get total number of permutations in Sn in n factorial. That is, order of group Sn is n factorial. So remember, order of symmetric group is n factorial. Suppose here we want to find the order of symmetric group 3, S3. Order of symmetric group of degree 3, that is S3. So order of S3 is nothing but 3 factorial, and 3 factorial is equals to 6. So order of symmetric group of degree 3 is 6. Okay, all of you get it this? So today we stop here. Thank you.